All right, so for our main speaker is Joe Dellinger, and Joe's been a long-time FBAC member and has been involved in a lot of things, mainly the A team, which is the asteroid, A stands for asteroid team. And so Joe was doing this 10 plus years ago. It was actually before I joined the club. And we're fortunate to have Joe. He started out in the oil business and geophysics and ended up here in the Houston area with his job. And Joe gained an interest in astronomy back when he saw a solar eclipse and a comet in his backyard in the 70s. And he's been hooked ever since. And Joe is a bit of a rabbit's foot when it comes to eclipses. So whenever he goes, the sky clears. So if you ever want to go to an eclipse, see an eclipse, find out where Joe goes, and that's where to go. So without further ado,
Thank
Joe
you.
Dellinger.
But it'll be a nail biter because it'll look like it's going to be cloudy, but then it'll miraculously clear just at the right time. That's been my experience. Knock on wood. I don't know. Haven't made any plans yet. All right. Oh. Yeah, this is just a photo I had handy. It's almost a joke that, you never see me in a tie. But I thought, well, okay, there you go. All right. Oops, is that the wrong direction? That's the wrong direction. Okay. So I really want to say thanks to Bill Dillon, who was the head of the asteroid team when I joined. So you can read a little article I wrote for the Tulsa Astronomy Club over there on the table, where I talk about being a brand new in Houston and discovering asteroids with Bill Dillon's team and how I'm just a groupie, helping them, and that all these people know all these things that I don't know, and it's very exciting. So I found that online. So we had a lot of team members over the years come and go, and the team started in the mid-90s, but I joined in 2000, and fortuitously just about the time we got the much nicer camera courtesy of the Zilka grant, which really helped things. And we pretty well were going gangbusters until about 2010, when it just sort of fell apart as just everybody got too busy and people switched to using online robotic telescopes, and and our telescopes tracking was getting worse and worse, and the sky was getting brighter and brighter. So it just sort of like the way things go. But we had a good decade where we were rocking and rolling. So I have several different sort of modules in this talk. So if you want to hear more, I can probably give another shorter presentation another time. But I wanted to emphasize more on, for this audience, what is it like to actually acquire the data? What are the steps involved? So I want to make it not be a mysterious process, right? I want to show you what it's like to acquire the data, process the data. What do you do with it once you process it? What happens next, etc. So that's the goal here. But I feel I should say, why study asteroids? Near Earth objects, I think, for me, was the big thing. The dream would have been to discover, a famous asteroid that was going to scare us. Not kill us, hopefully, but scare us. We didn't, but we found some cool stuff. So Hermes is the classical near Earth object. It was discovered in 1937 by some Germans. They only followed it for like 2 or 3 nights. They tried to get the word out, but nobody else saw it but them. And then it was just lost. Why is it historically significant? Because until then, people just sort of thought asteroids are boring. Vermin of the skies was a term that was used. And they didn't just see much point to them. And I would give an analogy. You live in a nice neighborhood in Chicago, and you know that in other parts of Chicago, there's like a murder a day. But you don't live in a bad neighborhood, so you don't really need to worry about that. That's never coming close to you. And then one day, a bullet comes through your front window, and you realize not all of the bullets stay in that other part of town, right? So astronomers sort of thought all the asteroids are between Mars and Jupiter, boring. And then Hermes went past, and they went, what was that? And we have one coming up even better. So Apophis, I think you might want to start thinking about plans now. So it is going to approach so closely on Friday, April the 13th, it'll get up to somewhere around magnitude 3. So here's a chance to see a naked eye asteroid. And it's particularly interesting to me because I did a postdoc at the University of Hawaii, and I was in the astronomy club there. And one of our speakers who would come and talk to us on a regular basis was this guy named David Tholen, and he would talk about asteroids. And at one of his talks, he talked about everybody's just looking out from the sun, out from the sun, out from the sun, thinking that there's nothing inside Earth's orbit, right? And he says, there could be asteroids that are dangerous to Earth that spend 90% of their time inside Earth's orbit in the direction of the sun. So he said, somebody needs to do a survey where they're not looking out. They're looking like as close to the sun as they can, like 30 degrees to 90 degrees from the sun. And so I heard him talking about why that was important and models and such. And then he actually got that funded and did that survey and discovered Apophis in it, because Apophis spends most of its time inside Earth's orbit. So that was really cool. And here's what Apophis is going to do in 2029. Here it comes by. And that ring of satellites you see is the geostationary satellites. The thing going around Earth, that's Hubble Space Station. I don't know why they, that's the ISS. I don't know why they included that. But there it goes by. And what you see is it's going to pass so close by, we're really going to yank its orbit something good. So in fact, we're going to change its orbital parameters totally. And here's the ground track, which is something you don't see much. So unfortunately, although it's going to go right over the United States, it's in the daytime. So somewhere off the east coast of the United States is where it goes from nighttime to daytime. So I don't know. I'm thinking, Canary Islands for the weather and the position, something like that. Anyway, I haven't figured out yet, but I want to see this thing, especially since, I heard about the survey before it was even planned, and Bill and I and other people, we helped chase this object when it was first discovered. So I have an investment in it, All right, this is a big picture. We did lots of asteroid hunting on a Saturday night after the public was gone. So here's an old-timey photo of the East Dome and the Research Dome with a big audience back before you had to reserve online 3 weeks ahead. People just show up. So sometimes we'd have 300, 400 people a night on a busy Saturday night. And then after 10 p.m. or 11 p.m., depending on the time of year, and the last visitors, you chase them out. And then we could set up the telescope for asteroiding. So what you see is here, that's a finder scope, which was this old rotting Maxitoff, but it worked well for a finder scope. What is a guiding scope. And there's our camera. And if you might be able to tell that that's the left side of Capricorn out the slit there. And one of the things we found was you really don't want any lights on. You bare minimum. So one of the things I'll get to later in the talk is we actually did some experiments, since I'm sort of like try to be scientific by training. And so we had these dim red lights on, and we just sort of assume that they don't cause any problems. And I said, well, let's do the experiment. Let's take some data with the dim red lights on and without the dim red lights on and see what happens. And oh, no. The dim red lights are not helping the data at all. So the red lights you see here, that's coming from like a very dim flashlight, so we don't crash into things in the dark. Oops, I'm going the wrong way. So here's a suggested experiment if you have like a teenager or somebody, or just want to do it for fun. Vesta is bright enough that it almost is naked eye visible. So I think actually now with the modern cell phone, you literally could hold the cell phone up to the sky and let it take one of those longer exposures where it tries to correct for your shaking of your hand. And I bet you could image Vesta. So it's almost bright enough to be naked eye. And here's two images I just took with a regular old Nikon camera, not a special astrophotography camera, like 10-second exposures. Again, this is the left half of Capricornus. Do you recognize it? And do you see Vesta moving back and forth? This is like 3 days apart. So it's right there. So anyway, one of the things I found interesting, I mean, back before about 2000, 2001, there weren't really that many people hunting asteroids. And you can really see this with Hermes. So they caught it in 1937 as it buzzed past Earth, okay? It came pretty close, not that close, but reasonably close in 1957. There was a pass in World War II times when they might have been able to predict it from the short arc they had, but anyway, they missed it. But then they also missed it in 1974. They missed it in 1986. They missed it in 1991. And this thing, as you'll see, is like not that dim, like by the standards of today. This is like dead easy. Like, and so that just sort of shows you how we were really not looking up before about 2000. So here it came by again in 21st October 2003, and that time it got caught. So the alert went out. Finally, we have recovered Hermes, last seen in 1937. Everybody jump on it. So I'm going to show you some data of Hermes, and I think it's interesting, especially for this group, to sort of see what the process data looks like and how you would hunt asteroids and what are all the things that you have to think about. So I'm going to use this as an exercise. So if you brought your laser pointer with you, get them out now, and we'll have a bit of a treasure hunt here. Okay, so just to give you some idea of how big a patch of sky you're seeing here, the moon would be about that big if it were in the field of view. And the funny thing is, I don't think we ever once took a picture of the moon with that camera. I never remember doing it. I don't know why not. We should have. Why didn't we? All right, so I need to explain to you a little bit about what went into this data. So if you, in the break, if you wish to, I have some sample log books over there, and the page that you open to where you see like the little yellow Post-it note, that is the log sheet for this night when we were acquiring this data. So you can look at what's involved. All right, so the tracking of the telescope absolutely sucked. So we would take 30-second images. And then if like they were all terrible, we would go get a heavy book off the shelf and wedge it into the telescope mount at various different points and try and get the telescope to stop doing that. So Bill will remember this. And we had several different books at different weights and several different places where we could wedge it in the mount. But even so, longer than about 30 seconds was hopeless if you didn't have the guider going. And so some of the times we couldn't get the guider to work, or we couldn't find a star or whatever. So we were shooting unguided this night. And so 30-second exposures. Now this was with the Zilka Grant camera. So it was a very nice camera in its day. However, it predates USB. So the way it connected to the computer was through a parallel port. And so it would take it a long time to download the enormous 2 megabyte file that the camera generated with each photo. So 2 bytes per pixel, 1024 by 1024. So exactly 2 megabytes, a huge file. And so it would take it 42 seconds to download that file. And so 30-second exposure, 42-second download, 30-second exposure, 42-second download. Okay, then we would throw out the 30-second exposures that were hopelessly badly tracked, which is maybe about a fifth of them. And then we would combine sets of those into stacks. So each stack here is about 3 minutes. So it's about 25 minutes worth of data, 30 minutes worth of data. And each stack is about 5 or 6 30-second exposures added together. And then we animate it. And I found this is about the right speed to spot things. Okay? And one of the tricks, so I wrote my own processing software because back then the commercial software was terrible. And my day job was writing processing software for seismic data. So writing software to process asteroid data was not that different. So in the evenings, I worked on programming to image processing for this, and in the daytime I worked on programming for BP doing seismic stuff. So programming. But anyway, one of the things was you would lose things. All the commercial software would, if you added things together, it would take only the stuff that was in every frame and show it to you. But then you lose stuff, right? Because the cameras did, dancing around. And so I put padding on it. So that's what you see there, why there's gray around it, and the image is vibrating around in that. Okay. So there's all sorts of stuff going on here. So an asteroid should move in a nice straight line, right? Because we're only looking at 25 minutes of time. So it's not going to do loop-to-loops or something. You're not going to get a retrograde loop, in 25 minutes. Okay, so do people have laser pointers? Nobody? A few. Okay, so here on the right are all the different sorts of things we can try and find in there. Okay, so who wants to try and spot something? Okay, go, Bill.
So, of course, this must be.
Did you shoot yourself with a laser? Okay.
So this must be Hermes.
Yes. Why do you think that's Hermes?
Because it's moving fast.
And it's
Not a big belt.
yeah, very good.
And then I spotted this guy.
Very good.
Yeah.
That's a main belt asteroid right there. Very good. And that was indeed Hermes. Yeah, you're too good. Let somebody.
I used to spend a lot of time doing this. And then there's two more right here.
Okay. Yeah, he's a ringer.
Yeah.
Trust me, with a regular audience, because I presented this sometimes if they have a cloudy night at the George and they desperately need a presenter to entertain them. Nobody spots it that fast, so it's a ringer. Okay.
How come the other objects are not moving on action? They've animated it for 25 minutes. Other objects, bright stars, and
Oh no, I'm tracking the sky. I'm tracking the sky. That
so stars on the ecliptic thing keep moving apart from the.
well, we're tracking the sky. I mean, the telescope is tracking the sky. I'll show you what happens if the telescope doesn't track. I have an example of that coming up. Yeah. Yeah. Also, what you'll notice is see how the edges jump all around in a crazy way? Because the software has lined it back up on the stars. So the stars are the fixed reference frame. Okay? Okay, so why do you think it's a camera artifact? Usually that is always the first thing people spot, and they say, oh, it's a black hole. All right, so a sign that it's associated with the camera chip is look at how the edges of the frame are moving around, and then compare that with how this thing is moving around. And so it is a bad spot on the camera chip. So in fact, if you open up the camera and look at the camera chip, you'll see like a blob of goo sitting on the chip. The chip is actually an inch square, so it's a noticeable blob of goo. So here's a brain teaser question for you then. Why would we buy a camera that had a blob of goo sitting on the chip? It's about 1/10 the price of a chip without a blob of goo. Yeah. So I believe this was a $10,000 camera without the blob of goo, $100,000 camera. All right. Okay, point one. Oh, very good. Usually my experience is nobody spots any of those. There's one. Yeah. Why do you think it's a cosmic ray hit? What makes you think it's a cosmic ray hit?
It's like a squiggle. Yeah.
It's like a squiggle. You were right. That is a cosmic ray hit.
Cosmic ray.
So that's a charged particle crashing into the camera chip from space. Yeah.
There's another one.
That's a galaxy. Very good.
That's a nice spiral.
Yeah. So can you find an elliptical? Yeah. Okay. So let's see. What did we last define? Satellite. Where's the satellite?
Really assuming that's going.
Okay. So why is it in two chunks in only one image? Stacking. Why the gap between the two bits of line? Downloading. Very good. Yeah, this is definitely a ringer. Okay.
Did we have any discovery? Were any of those figure ones discoveries?
So what I did here was I stacked this at sort of an intermediate. So basically, I would shift and then stack. So you could process the data all sorts of different ways. So what I did here is I'm shifting a little bit, but not too much. So the main belt asteroids are probably being shifted a little bit too much, and Hermes not quite enough. Because I didn't want to smear things out too much, but you might be able to tell the stars are all a little bit smeared out in the direction that Hermes is going. So if you want to get dimmer objects, then you need to cut thicker wedges of data, so you go deeper, and also stack slower. So this is a too high a speed to be a good stack for these objects. So none of these objects were discoveries. However, as I recall, there are actually like 11 objects in this field. So one of the things that I want to do in the future, but ran out of time for this presentation, was to go back, get this data back off DVD, and then show you for comparison the stacks and we then did discovery. Because if I remember right, there were 11 asteroids in this field and like 3 discoveries. However, none of them show up in this image because we've sliced it too thin and we don't have the stacking shifting at the right velocity. Okay, so I think that we've pretty much hit everything. Okay. Could you, Bill, your services are needed. I don't know. I'll show you. Can you? They're hard to spot. So are we ready to go to the answer key? I think we're ready. So if you didn't have enough laser pointers, I would have done this. All right, so there's the NEO asteroid. Okay. Main belt asteroids, did you spot all of them? Even this one was right on the edge of what you could discover at that time. As I recall, this one was not a discovery, but it was of about the bright end of what could still be discovered at that time. For us, like a magnitude 17 was like super bright, no problem. You could image them right through thin clouds. Most of our discoveries were like about 19.5. Lots of stuff to discover at 19.5. And then if you could go like really beat the hell out of the data and could get to like 20.5, oh, there's discoveries everywhere. But then you like, do I really want to discover that? Because it like takes like 30 minutes a stack, to get a point. And the most extreme thing we did just for fun was we imaged Sedna, which is like magnitude 21 something. And basically, it took like an hour and a half of data to get 1 point. And then you had to image it like week after week after week to see the motion, because it moved as much in a week as a normal asteroid did like in 10 minutes. So anyway, there's the galaxies. Did anybody spot this other galaxy? There's a satellite. You got that one. Nobody spotted this, but yeah, you can see there's something going wrong with this star and also this star and this star. It's because it's too bright. It's clipped. Okay, there's the camera artifact. Okay, cosmic ray hits. You saw a couple, but there's actually 5 that I could spot. The interesting thing there is, so this is like 25 minutes worth of data, and there's a cosmic ray hit somewhere on the chip about every 3 minutes, right? Because each one's about 3 minutes. So that means as we have been sitting here talking about this, how many square inches of surface do you each have on you? You've probably been hit like 15, 20 times as we've been sitting here talking.
I did a 1 hour, because I took a 1 hour exposure, and it was inside my house, camera pointed at the ground. It was full of cosmic rays.
Yeah. So I call these things transients in that it's just like, what is this blob that sort of seems to be trying to form, and like this dot just appears in one frame. A dot appears in one frame. I don't know what those things are.
Could be a cosmic ray getting perpendicular to the chip.
Should be. All right. Anybody want to guess what this is? Don Wells took this picture. So what common object that you see in the nighttime sky will do this to your data? That's an airplane. Yeah, so what you see is it was coming in for landing. It had the landing lights on, and then the strobe went off, 3 strobes, and then they lit up like some area of the plane around that made this Romulan spacecraft shape. But anyway, that's a fun picture. All right, so now I'm going to show you what it's like I should use the past tense, setting up. So there's the East Dome with the beautiful, Houston glow behind it. And the first thing you need to decide is where are we going to shoot tonight? So Bill Dillon usually would send us marching orders, and here's the sort of research he would do. So you get a file from the Minor Planet Center where they list all your discoveries, and then they tell you which ones need observations. So basically, this opportunities, and then they list when it'll be at opposition. And if they put the numbers out here, they're basically saying, we'd sort of like you to get some more data points on this. And you can see how long the arc is. Like 6 oppositions means it's been hit 6 different times, going past Earth, so 6 different years. 11-day arc, well, okay, that one really needs another point soon because this is from 2008. Orbit none, you're screwed. That's lost, probably, unless it's really recent. So one of the best things to do was pick one of your known objects from a previous year that they're requesting observations on, because it's obviously in a bit of sky that nobody's hit, right? Because if somebody else hit it, then they would have a data point on it and they wouldn't be requesting you to observe it. So there may be other stuff around it, right? Or if you had 1 or 2 points from within a few days before, that's a good one, because you need 2 nights on an object to officially discover it. So the sequence is you observe it once. That's called a one-night stand. You generally don't get any credit for those. Then you get a confirming night, and if the data looks good, then they'll give you what they call a provisional designation, and that's something like 2000 P08, a year, a letter that indicates which half month in the year it's in, and then the letter cycles A through Z, and then a number after you've gone through the alphabet once, 0, 1, 2, 3, etc. All right. So that's the sort of sequence. Wrong direction again. They would publish a sky coverage chart where you could see where people had been turning in data. So that's what the sky surveys were like back in 2008. So there were some robotic telescopes by 2008 vacuum cleaning the sky. You see one was like following a line of declination, another one was going along parallel to the ecliptic. And so you could sort of see like, oh, wait, they missed a spot, they missed a spot, and you could punch in there. One of the things we could do for a while was observe south of declination -30, because pretty much nobody was doing anything with that. And eventually Australia fired up, but for a while we had this window from about -30 to -36 that wasn't too far south that we couldn't image it, but nobody else was there.
Once with the ecliptic being that far south, which increases your chance of finding something in the summer Milky Way.
Yeah.
So there's kind of 2 things working against us. So sometimes we try to image in dark clouds, dark nebula in the background, cut the number of backgrounds.
The problem is then the asteroid would leave the dark nebula and then go through Milky Way. Yeah. So we had some times where Andrew Lowe in Canada, I'll mention again later. He had discovered an asteroid like at a photographic survey or something. And then he said, oh, please, it's back in opposition. Get me a point on it. And it would be like right deep south, Milky Way central. So we literally would have somebody, running the telescope and then writing the data to zip disks and then running them downstairs to where I would be with my computer processing the data on the fly, and then I would come back up and say like, okay, the asteroid's going to be in a clear spot in 23 minutes. Because it would just be like next to a star, in a star, in a star, in a star, and I could see it and sort of sketch on the screen and see there's a hole, and when is it going to hit it? So literally they would be shooting and jumping around fields, and then I would be processing the data downstairs and then giving them lists of times. Get back on that field exactly at this time. So anyway, that was sort of crazy, but it was fun. This is what the camera looks like in the box. You really want to keep the water out of it. I'll show you why in a second. So like layers and layers and layers of hermetic sealing, and then desiccant, lots of desiccant. And then you put it on. So there's the guide scope and the camera. And you have to run the cables very carefully so you do not step on them, because if you stepped on the cable, it would briefly short the cable out and the camera would throw an error and refuse to function anymore. But you couldn't just unplug the camera because then it would do an uncontrolled warm-up, and the camera chip was so thin that they said if you let it do that, it would fracture and you would destroy the camera. So you would get the dreaded camera error -13, and then it would refuse to take any more pictures until you rebooted the computer. So you would have to warm the camera up, reboot the computer, reestablish control, and take it back down again, and that would take about an hour. And so you felt really stupid that you stepped on the cable and like, now an hour of nothing as your punishment. We used a batten-off mask to focus, and this is what focusing looks like. You would basically tweak the focus in and out, and when you got this nice shape with 3 lines all crossing through the same point, you're in focus. We did for a while have a robotic focuser, and that was really convenient. It also turned out it wasn't that good a focuser, that this method was clearly better. So eventually it turned out the robotic focuser had 2 plugs in it, and it said, be very careful never to plug the wrong cable in the wrong pole. And one time we did it and dead. And then we were like, well, it sort of sucked anyway. So then we find a guide star. So we had a special purpose little box with a computer in it. And we had to guide with about like a ½ second to 1 second interval, which meant that we needed to find a pretty bright star. So we had the guide scope where we put some knobs on it so you could actually turn it over like 5 or 6 degrees, because you had to look around and find. No, you had to find a good bright guide star. No, well, maybe seeing would be a problem if you had a telescope that wasn't dancing the waltz. So anyway, so this is what the raw data looked like as it came in. So this is what you'd see on the screen. It only happened a handful of times where we had an asteroid bright enough that we could just see it in the raw data on the screen as the data came in. Yeah, well, you even stretched. This is the best you could do. This is what happens if you stop paying attention and like went outside and were chatting, that the telescope would stop tracking and go. So this is what happens if the telescope stopped tracking for about 5 seconds. So that's what the stars would look like if we weren't trying to track. This is what happens if you don't change the desiccant once a month. As you got it down to temperature, suddenly this ring would appear and cover most of the field of view. It's very disheartening. Okay, so now some science. Okay, how to acquire data. So I occasionally join some of the other research teams We did have some other research teams. So for example, there's a supernova team, and they were chasing supernovas, and I joined them a few times, and they never discovered any supernovas. And I think I know why. Because they would wait until the sky cleared to start setting everything up. And then when they got it all set up, the sky would go cloudy again. And then they would start talking, and then the sky would clear up again, and they would keep talking. And then they would say, okay, let's get shooting again, and then the sky would go cloudy again. So I'm not meaning to be too harsh, but it was fun. They were having fun. They were doing what they wanted to do. But what I would tell people was, when the sky is clear, don't talk, shoot. You can talk when it's cloudy. You can't wait for a clear interval to begin your setup. You have to sort of judge, yeah, let's risk it. And so actually the most productive single night I ever had, where I think I had 18 discoveries in one night, if I remember right, I can't remember. Anyway, it was a lot. Was a night where we had like a public event for a donor, and they wanted to show them stuff, and it was totally cloudy. And then everybody went home, and I thought, I think it might clear up. And so I set up the camera, and just about the time I got the camera cooled and all ready to go, clear. I shot one field for an hour, and then whoop, back to cloudy. And then there were like 18 discoveries in that one field or something like that. I can't remember. That's probably exaggerating that, but there was a lot. And it was the most productive single night I ever had. So yeah, if I had not sort of looked at it and said like, no, I think it's going to clear, it wouldn't work. Always have 3 clocks. Why not 2? Well, what if they don't match? You want 3. So, and I'll tell you why in a bit, why you want to have 3 clocks. Take darks at several temperatures, then run the camera as cold as possible. I know that's not standard, but for our hot climate, that's what worked. And then I'll tell you a bit more about that in a second too. Don't fritz out that all the stacks have to be the same length. No requirement that the stacks have to represent continuous shooting with no gaps. If all you get is cloud holes, shoot in the cloud holes. If the tracking gets worse, cut the exposure time down to 30 seconds. If the tracking starts getting better, try a minute, minute and a half. The telescope was not, and the weather were not good enough that you could just sort of go out there and set up and get on the field and then say, I'm going to shoot for an hour, 60-second exposures, and go, take a nap or something and come back and it's done. No. You're not paying attention and dynamically adjusting to the changing conditions, you're really hurting yourself. We learned to do experiments. We learned that even dim red lights in the dome damage the data. We found shooting flats, really, you didn't really need a flat from like that night. You just needed a flat from like that month. And we had all these experiments we did with, we put a blanket over the telescope and shot at a light, and we had like this screen that was supposed to be uniformly illuminated, and so everybody swore by different things, and I said, let's just try every combination, reprocess the data, look and see which makes the best data. What worked was, when the first or second night that you're out there in the dark moon, so you get like one field, and then this big, bright gibbous moon comes up and lights up the research dome, and then you point the telescope at the research dome and take your flats for that month, and then go home. And that worked better than anything else. Optimal exposures were about 30 seconds to 3 minutes. You sort of had to learn to adjust the exposure length with the sky brightness. So basically, the brighter the sky looked, the shorter the exposures you needed to use. So theoretically, the camera was supposed to be completely linear. I would say the experimental evidence was that was not true. That you needed to keep the camera sort of in its linear zone, which was maybe at most like 1/3 to full pixels. Above that, yeah. If you could see any hint of the Milky Way, good night. And even if you had a big bright moon, as long as you didn't have any beam of moonlight actually going in the telescope. So if you could like move the slit, even if you were slightly occulting the aperture, just don't let any moonlight go in the scope. And if it was a nice, transparent night, actually we discovered at least one asteroid on the night of a full moon, and not that far away from the full moon. This is something people would tend to screw up on. You have to keep good notes. So you can see over here these black folders if you want to see what my notes were like. I brought some examples. So if you get home and you're like, oh, what was this data? What field was that? Your host. So it happened a few times to people. They got home and said, like, I didn't take good enough notes. I just can't do anything. The night was a waste. That was embarrassing. Anyway, don't forget to dither. So basically, there are some little bad spots in the camera chip that will look like asteroids. And with the telescope sort of gradually flexing or something as you shoot, you would get these hot spots to move nice and linearly, like an asteroid, and you would turn them in, and you know what? They were always discoveries. A hallucination is always an unknown asteroid. And the Minor Planet Center keeps track of when you turn in something that nobody else, who turned in data around there didn't see that. And like if you look suspicious, they can just say, hey, you're on notice. And if you keep it up, there's like, we're done. We will never take data from you again. Bye. So we really didn't want to get blacklisted, especially as we were, amateurs, like clinging on by our fingernails to being allowed to even participate. 1 second clock accuracy is required. One of the things we learned was don't reset the clock. Leave the clock alone, because Microsoft does not like you if you reset the clock. All sorts of weird things will happen. The clock will come unglued and start jumping around and doing crazy things. And God help you if you try and install software that's like going over the internet to NIST and trying to keep the clock perfect. Oh, your data is destroyed. You have random clock glitches of 30 seconds everywhere in your data. It's useless. So what you do is you have your 3 clocks, and you see how much off it is, and then you periodically check it, but you can't like open up the clock window and shut it again, because that actually changes the clock. So anyway, what you do is you take the data, then go look in the headers of the data and see that the times are what you expected. And so if the offset at the beginning of the night and the end of the night are different, then there was a clock glitch somewhere in the night and you have to find it. But if it was the same, then you're pretty good. So that's this DT plus 10 saying the computer clock was 10 seconds fast. Okay. Standard processing, I'm not going to talk about much to this audience because you all know about it. Darks and flats. They depend on exposure length and temperature. I wrote my own software to clean up our images because there were all sorts of different kinds of garbage in there. And what I found is you come up with an algorithm that will attack the worst layer of noise, and then you lift that off, and then you discover a different kind of noise underneath now becomes the worst layer of noise, and then you attack that, and you keep going until you can't make any further progress. So basically remove hot pixels without removing hot stars. Remove gradients, remove stripes, align things, discard badly tracked images, discard images too affected by clouds, and then you group the remaining images and make stacks out of it. Some innovations at the time was to do a moving stack, so you could put in the expected motion for the asteroid, and then it would smear the stars and not smear the asteroid, which was helpful. And then you can reprocess the data. So one of the things you do is you see something and you pick it, and then now you've got a velocity for it. Then you go back and restack with that velocity and see if it gets sharper and better. So we would do that sometimes. The reason I said take darks at a bunch of different lengths and such on darks at different temperatures is basically it turns out it's pretty simple math. You just say, what combination of these darks minimizes the noise in the data? So you can solve that. It's a nice, simple equation. So basically, I don't know anybody yet does that. Maybe that's finally caught on too. But basically, I would generally shoot a set of darks at the beginning of the night and a set of darks at the end of the night, maybe a set of darks in the middle, And then I would have these darks, and then I would give them all to the program, and it would find what linear combination of those darks best dark subtracted the data. And that did noticeably better. And it also meant that we could just always be running the camera as cold as possible. The cameras back then were much, much better the colder they got. Non-interactive processing is vital. The problem with the commercial software is everybody wanted a nice GUI and go click and get an instant response. And so with all my tricks I knew from work, I could process one image on the fastest computer I had available to me of the day in about 30 seconds. And so I wanted to make it a batch process where all these different steps, for the most part, the software did. So I would start it running and then go eat dinner, take a walk, do laundry, whatever, and I'd come back an hour later and it'd be done. And then I could look at it. So this was an example of processing using commercial software. And if we were blinking it, the whole thing would be getting brighter and dimmer and, you know, distractions for your eye everywhere. And this was the result from my program. So do you notice that it's actually blinking? Did you notice? Is that the software did a good enough job lining everything up and getting everything at the same level that unless you're really paying attention, like you can see the black hole here is actually moving around a little bit. And this thing appears. I'm not sure what that is. Is that a satellite or meteor? I think that's probably a meteor, but anyway, did anybody notice a moving object? Yeah, very good. That's the third rocket stage of Apollo 12, which is another whole story that I do not have time for tonight, but if you want to hear the fun of the chase of the third rocket stage of Apollo, that's another story for another time. All right, so how much more time do I have left?
10, 15.
Okay, perfect. Okay, so this is what the process data looks like. And so you basically pick a window out of the field of view and you blow it up. And then you look for moving objects. So if I could get you, Lee, to click forward, and on frame number 5, there'll be a button at the upper right that says loop. And so if I can get you to just loop it a few times. So if you click, it should go forwards. And then you'll see the word loop appears. So click the loop, and that'll take it around. So just go around a few times. Now we'll see, Bill, okay, can you spot 4 objects? Okay, you see one? Yeah, point it out. Yep, very good. Top right? Let's see. Yeah, I like it to go a little faster, but yeah, the next time just hit done. Okay, hit done now. There's the objects. All right, so once you've identified them, then you use software. So in the early days, the software was like really fiddly. You had to get the image aligned, and then it would like put up a little star chart, and then you had to go tell it this star is that, this star is that, this star is that, and it was really painful. So this software was so much nicer. If you could give it pretty tight bounds on the orientation and magnification of the field, etc., and then it would, and position, and then it would pretty reliably recognize the star field, and then you could pick things. So here we pick this, and it basically fits like a little Gaussian blob to it, and it tells you a magnitude and a position, etc. So here's the RA and DEC it calculated for it, and it says that's magnitude 18.5. So then when you're all done, this is what it outputs. So it populates a header here, and you see William Dillon is our fearless leader, so he's the contact. And then it has a set of observations for each different object, and the star means that's the first one of that set. The 735 here is our observatory. That's our code for our observatory. This is the brightness. This says it's in the red band. And this is the date in decimal day to 5 places of accuracy, which is about a second. And this is the RA and the DEC. Okay, so and if you turn that in, you will be very sorry because you'll probably have some screw up or problem in there. So what you need to do is then do your own QC checking before the Minor Planet Center's QC checking. So you run a little program, and it basically fits a motion, a linear motion to your data points, and then it tells you the time offset, the RA and DEC offset, and the error to that fit, and then it'll find which one seems to be the outlier and throw it out, and then do a fit with the rest and show you. And then you look at it and go like, okay, so theoretically, if you're within 2 arc seconds, you're good, but it's better to be within 1 if you can. And they generally want 3 points. And here's an example of what can happen. So this object, obviously, we had some problems with, because it's noticeably, for that bright, an error of 1.25 arc seconds is pretty bad. So that's suspicious. So what do you do in that case? Well, what you do is you go back, you look at the coordinates. So basically, this is the coordinates in pixels on the screen where that object was. So you see object N. And then you restack the data with that velocity that you just determined, and you look at that particular object, and you may make one of the stacks thinner, one of the stacks thicker, etc. It was too close to that star. Let's throw that one out, and you restack it. And what you see here, big X. That means when I went back and looked at it and processed the data more carefully, the object disappeared. So it was just a happenstance alignment of noise. Then you go to the Minor Planet website, and you can give it that file, and then for each object it'll tell you if it recognizes it. So for example, this one here, oops, I hit the wrong button. This object here, the offsets of 0 and 0, that's 2004 VJ16. Which was our target. It was a discovery of ours from 4 years before. So great, we got our target. And then here, what you see is there's no object nearby. The closest objects are like 10 arc minutes, 10 arc seconds, or no, I think that's arc minutes. 10 arc minutes away. So that's a possible discovery. And we did get credit for it. And I went back and looked to see what happened to it last night. It turns out we lost it, because what happened was as the orbit got longer, they linked it back to an object from several years before that had a longer arc, and so we became the recovery of 2004. Ow! Which is fitting, because it hurts when you lose one. And then the other discovery turned out to be 2001 SH29, and what you see is, last observed on 2001 November 16th, and here we are in 2008. So basically, this object was lost in space for 7 years, and we recovered it for somebody. Yay! We rescued this object, and here, once they calculate an orbit, you can ask for the misfits. So it's good to see if you're really keeping up. And so this is all the different observatories. 704 was a big robotics survey run by the U.S. military. So you see they did a lot, and you see they just hammered this object in 2001. So this is the misfits in RA and DEC in arc seconds. And you see they got this object September 19th, 2001, September 21st, 2001, again and again and again and again in 2001. Then somebody got a lone night on it in 2007. That's a one-night stand. And the Minor Planet Center was not able to realize that that object connected back to this with just one night. Then we got a pair of nights on August 26th and August 30th. And then with that data, they linked everything back. And this is the one that won, not us. But you can sometimes get lucky. So here's the night where we got the luckiest on that. So this object, 2008 LU7, here's our discovery night. So 2008, June the 3rd, Here we are, code 735. Okay, and here was our confirmation. Linear hit it literally like hours after we did. Well, they were in New Mexico, so they were probably chasing it, as the world turned that same night. So we stole it from Linear, and we went back and hit it again in June the 5th, June the 8th, June 11th, because we didn't want anybody to steal it back from us. But look what happened here. Okay, somebody saw it in 1995 on one night. Somebody saw it in 2002 on one night. Somebody saw it in 2003 on one night. Somebody saw it in 2004 on one night. So it's just all these one-night stands that they couldn't connect together. Then look what happened here. 2007, January 17th, February 9th, February 24th, May the 3rd, May the 14th, May the 25th. Just too far apart that they never linked, like these things like a week apart for the same object. It was just enough that they never linked this together. So all these observations, they didn't link it together. And then we lit the fuse with this pair of observations, and then it all linked back. Except it didn't, because originally they awarded the discovery credit to Linear. And so, feeling bold, I actually emailed them and say, like, hey, what was wrong with our data? I don't see anything was wrong with our data. We got ours in earlier than they did. Like, why did you give credit to them? And I was expecting they wouldn't answer, or they would just like, buzz off, you stupid amateur. But instead, what we heard back was, no, you were mistaken. This was the earliest. What are you talking about, a June 3rd observation? You did not have any June 3rd observation. I'm like, yes, we did. We turned it in. I'm like, oh, the email must have gotten lost. We never received it. And I was like, here is your reply saying that you acknowledge receipt of that observation. And then they went quiet for 2 weeks. And they came back with this email. So, we have remedied your situation. You're now credited with this discovery. The error was on our end, so no harm should be done to you. It took a bit to track down, but it should be fixed. So then I got another email from them, which I don't have here, where they basically said, like, thank you, because it turned out we were dropping, like, about 1 out of every few hundred observations on the floor. And it had been going on for some time, and you were the first ones to notice. And it was like a really insidious bug and took us 2 weeks to track it down. But thank you. You saved all these observations from getting lost. And sometimes you get something interesting. Here's one of the more interesting objects. It's not a near Earth object, but it's a near Mars object, maybe George. And here's a Mars crosser, which we named for Carolyn Sumner's. And I like these. I seem to have a knack for discovering Hungarias, which are these really super tilted objects just outside Mars's orbit. In retrospect, it's because I would go like, oh, goddamn, another field with 18 movers in it. I'm not going to shoot on the ecliptic again. So I would shoot like 40 degrees off the ecliptic. And I'm like, oh, no movers in that field. Ha, done. But then if you did get something, it's like, oh, that's cool. So yeah, I found that I tended to shoot more and more fields at wide off the ecliptic looking for something interesting. But then you do that, you discover Hungarias, it turns out. Here's a Trojan. We discovered several Trojans. They basically chase Jupiter in its orbit 60 degrees ahead or 60 degrees behind. And this object I really treasure because it has an eccentricity of 0 and an orbital inclination of 0. So I named it for a friend of mine who was famous for his level emotions and phlegmatic attitude. We had some various adventures, so you can name things. So we named one Brazos Bend. And we tried to name one Crikey after the crocodile hunter guy, and it was rejected. And in those days, actually, you could contact Brian Marsden, who was on the committee, as like a permanent member. The others rotated. And I was like, okay, Brian, what was wrong? Why did you reject this? And he said, I thought Crikey was a wonderfully imaginative name. Some CSBN members, however, were opposed on the grounds that it was flippant. And even that, according to the OED, it is a euphemism for Christ and therefore blasphemous. Steve Irwin would just be mundane and boring. I think some of my CSBN colleagues need to develop a sense of humor. Maybe I'll try and bring it up again. And I got an email from him a few months later saying, I convinced them, and so there is an asteroid named Crikey. So thank you, Brian. We collaborated some with JPL. So for example, we would get emails, you know, we're doing a planetary quarantine analysis for the Deep Impact rocket third stage. You know, can you go chase it for us? So here is the third stage of the rocket of Deep Impact. Like, you know, a few weeks after launch. I'm getting close. And we chased NEOs. So here is our data on Apophis. I didn't list all the data because obviously there's gazillions of them, but we were one of the ones who contributed to its orbit. And we collaborated a lot with Andrew Lowe. That's another whole talk of stories about our collaborations with him. But Andrew, what I will say is, if you read that, you know, they discovered an old archival observation of this dangerous object, and now they've nailed down the orbit and it won't hit Earth. The person who finds those is Andrew Lowe. And he's a Canadian amateur. And he is the best at the world at finding asteroids on the internet. So he doesn't use, you know, he uses robotic scopes some, but he mostly just goes through online archives of plates and finds streaks. And then he has this amazing intuition, like, I'm guessing that that's a Hilda, you know, in which case I might find it on this other survey, you know, 2 years later when it, you know, and then he goes, oh, there it is. And then he'll start to connect it together until he'll have like 4 or 5 points and then go like, yep, I got it. You know, so he's amazing. I mean, his intuition at guessing the orbit of an asteroid from one stupid little streak he's magical. This is our current status as of last night. So we had 305 unnamed and 52 named main belt asteroids and 4 Trojans. And I wish we would have discovered some of these other things we tried, but oh well. You know, most asteroids are boring. So here is our most recent name that came through, Knaus. So hopefully Tracy is actually online and listening.
Yes.
So anyway, I'll tell you the story of Knaus here in a second, and Bill can chime in because he's the discoverer, not me. Thanks to Leonard for helping to write the citation along with Bill, and we worked on this for a while. So Tracy Knaus, born 1964, is an American amateur astronomer well known in the Texas amateur community for her meticulous sketches of deep sky objects. She is director of astronomy at the George Observatory in Needville, Texas. Tracy continues to share her passion for the night sky and inspires others through her enthusiasm, guidance, and friendship. Discovered 2000, August the 6th. So it's a Hilda, and this is the discovery circumstances. So it was discovered almost at when it was the furthest from the sun. So a Hilda is in an orbital resonance with Jupiter. It basically goes out and visits Jupiter's orbit. And when it does, Jupiter is either 60 degrees ahead, 60 degrees behind, or on the other side of the sun. So it visits Jupiter's orbit, and Jupiter is never home, which is why that's a stable orbit. So it gets as bright as in the 16s at a perihelic opposition. So I'm hoping that Tracy will actually be able to see her asteroid with her own eyes with the big 36-inch telescope. So how did this happen? So you all might remember there was the NASA Deep Impact mission to Comet Tempel 1. And so they're going to whack the comet with a big hunk of metal and blast it. So they wanted amateurs to take pictures of it before they blasted it. And so they put out pairs of nights a month apart where they wanted everybody to jump on it. And I will remember the night because it was a Saturday night, and Bill, Cynthia, and I were there. And we shot like a couple of asteroid fields while we waited for the comet to come up because it was like way, way, way before opposition. So it didn't even, come up until like 2 a.m., something like that. And I was flying to a conference the next morning. So I stayed and saw one image. There's the comet. And I'm like, great, I've seen the comet. Okay, I'm off to Calgary for a convention tomorrow morning. Bye. And then when I get back, my email is blown up because Bill, I made observations of Temple 1 early on the 8th, and I have your object and all my images. So what happened was, basically a couple days later, Bill, looked at the comet, and they realized, wait a minute, there's something else moving there. And they're like, oh my God, an 18th magnitude asteroid, like 2.5 months before opposition. It's got to be a known object. It wasn't. It was an unknown object. So then he was like, oh no, all these other people have this data. I'm going to get scooped. So he turned it in, and it turned out, well, perhaps he wasn't as diligent as he could have been by waiting for 2 days, but he was more diligent than anyone else. So he got the discovery credit, and then the nice thing was, remember, you have to do follow-up, right, for it to count. NASA put out the word, hey, everybody who was imaging that comet, go see if you can spot this asteroid in it. And everybody like, oh, there it is. Oh, there it is. Oh, there it is. Oh, there it is. So anyway, the MPC has spoken. Looks like this distant object could be in a 3-2 resonance with Jupiter, and that's the initial orbit. So you see all this August 4 to 10, that's all the people observing that comet. So it turns out, here's the story I told you about clocks. So it turned out that the night before, Friday night, K2 had gone out and photographed the comet. Okay, so some of the emails were saying, like, wait a minute, the initial orbital fit is hyperbolic. And Bill was very excited that, like, is this like a visitor to our solar system? How can it have a hyperbolic orbit? So with the benefit of hindsight, I was able to go back and look at the observations and look at the residuals, and K2's observations were all off. He had a clock error. That's why the first orbital fits were hyperbolic. His clock was probably off like 10 or 15 seconds. And that was enough. And so if you look at the residuals, you will see that even if K2 had turned in his data first, Bill's night probably would have scooped it for the discovery because K2's data had 2 high errors, and they would not have awarded the discovery credit to that night. So that's why 3 clocks. That's why being paranoid about the clocks, because an error of like 10 seconds is enough, your data's screwed. Anyway, so I wanted Tracy to see a discovery image, and so I asked Bill, can you find me a discovery image? And he's like, it's from 2000. Are you crazy? But I went through my email archive, and thank you for CCing me on your communications with NASA and the Deep Impact Project, because I saw that NASA requested Bill to put his discovery image online so they could make a little press release about it. And he said, I'll make a little web page for you, and you can grab it from there. And so then I went and found the URL in that conversation, and then I used the Wayback Machine at the Internet Archive, and I discovered that they snapped the page once, but once was all I needed. And I downloaded it, and here is that web page that Bill made for the NASA people to link to. And here it is, a snapshot of it in 2009. And I would say, don't try and go to that BillDillon.com now to see if it's still there. It is a gambling site. However, here's Temple 1 and the asteroid 2000 P08. So congratulations, Tracy. We wanted to save a really special one for you. This was by far the biggest asteroid the club ever discovered, estimated size about 20-25 kilometers across. And it regularly, every few years, gets up into the 16s, so you actually have a hope of seeing it visually, which we thought would be important to you. And it's got an interesting orbit to boot. So thanks. That's it for tonight.